All right. So today we're gonna continue our discussion of non-abelian gauge theories. Part two of this course, section two of this course, part two of QFT. And we're gonna be focused on the quantization of the path integral quantization of non-abelian gauge theories. Right? So that's what we're going to be talking about. In particular, we're going to talk about the Fadeev-Popov Lagrangian. Yes.
Sorry, this is just a quick question. When we kept mentioning how 2D has like positive beta functions, right? So it doesn't really exist as an interacting theory. Is QED going to be like saved by say interacting with these other
Yes.
theories at all?
Correct.
Okay.
QED sits inside standard model of particle physics, right? So, and there is, if you just look up the Nobel Prizes, you will find Veltman, Taouf, and a whole bunch of people got the Nobel Prize for proving that that standard model of particle physics is renormalizable. Right? So it is saved. How? There's like there are new degrees of freedom. QED sits inside the SU2 of electroweak, right? Non-abelian. Well, there's SU2 times SU3 times U1. That group is fine. Right? So standard model of particle physics is renormalizable. It's good. It's a sensible theory. Yeah, it's good. Very good, very good. All right, any other questions? All right, so review of lecture 11. We're gonna discuss that actually. In search of 4D quantum field theories interacting QFTs, we turn to gauge theories, right? So we know that U1 gauge theory is not going to help us. The reason is that photons do not self-interact, right? Abelian gauge theory is free. Pure abelian gauge theory is free theory. So if there is any hope of an interacting theory, it should come from coupling to matter, to fermions, right? Charged matter, right? The simplest model of that type is QED, right? When you couple them to fermions. But the interaction in QED is irrelevant, as we showed, right? We calculated the one loop beta function, it came out to be positive, and it is irrelevant. QED has a Landau pole, so it doesn't exist as an interacting theory. You remember what Landau pole was? Anyone? It's a scale at which naively, at some finite UV scale, naively the coupling is blowing up. But that's not trustworthy, reliable calculation because you do this in extrapolation to non-perturbative regime from perturbation theory. All right, what about non-abelian gauge theories? Non-abelian Yang-Mills is self-interacting, so we could study it on its own and try to see if it makes sense as an interacting theory. We could also couple it to matter, to fermions in particular, and we end up with a theory that's called QCD, the simplest way of doing it. We're going to end up with a theory that's called, for SU3, right? It's going to be quantum chromodynamics. This is a theory that's relevant for nature. SU2, the simplest group that we're going to consider here is going to be SU2. That's also a theory of nature that's electroweak force. So U1. Yeah, okay. Yeah. All right. So that's what and I already gave you the punchline. Non-abelian gauge theory is going to save us. So in the interest of, I think, not all of you guys were in part one of the course. I'm going to review stuff that we went over in QFT1. And just to make sure everybody is on the same page. In the interest of time, I'm just going to review the geometric picture that now put next to this nonlinear sigma model, and ON model gives you a nice picture, right? Because we had a long discussion of what gauge theory is, right? Where its origins are. So what was the geometric picture? It was a fiber bundle, right? It was a principal bundle. What we have is you have field theory, so it's a map from an internal manifold, from space-time to an internal manifold. This is the field manifold. right? So the field at each point in space-time takes a value in some internal manifold. The case of symmetries, right? Where the case of the symmetries that we studied quite a lot, where these continuous symmetries, where we had Lie groups. So X is a Lie group, right? These are differentiable manifolds, they're very nice. And we learned that Lie groups are, if they're compact, I can just, well, we discussed this in the topology of them in detail, but you can learn quite a lot by looking at the tangent space, which had a name.
Yeah.
Lie algebra, good. All right, so examples of these Lie groups is U1, which is topologically, what this X is just S1, it's one-dimensional circle. SU2 is S three-dimensional sphere up to some subtleties. There's UN, there's SON and SUN that we discussed in detail as gauge as gauge theories, classical gauge theories in part 1 of the course, if you recall, right? We discussed how there is really the representation theory of all of these are related. All right, so what is the field? The field takes a value in this manifold. So phi I of X is the value of the field that we imagine at this point. It's like here, this point. At this point, it's taking this value. It's a vector somewhere. Now, because this is a Lie group, I can take this point and move it around the group, right? By the action of the group, this point moves around, and that is just a unitary unit. There's a unitary. We're talking about unitary representations, right? We're acting with a unitary. Do you remember why? Why unitaries?
We understood.
Yeah. These are unitaries in the Hilbert space. But if we are not worried about the action of them in the Hilbert space, if we're just abstractly talking about representation theory, it could be any representation matrix. So there's some sort of a Uij of X that acts on phi j, repeated indices are summed over, and this whole action occurs at every point in space-time. We said that global symmetries are where this Uij is independent of the space-time point, right? So you take at every point you have a fiber, right, which is this internal. This X is sitting at every point. And you take all the vectors and move them the same way by the same angle or same action at every point in space. That had a name. That was a global symmetry. Gauge symmetries was not gauge transformation is not a symmetry. It was an action that you could apply at every point separately in space-time, right? That's why there's an X here. An example of this was U1, which we saw, if you don't know anything about QED, right? That's how actually we started. We said we have a psi X. This is a fermion, and we saw that these are complex fields, which means that I can multiply them by e to the power of I alpha X. It's a phase, right? Now, if I pick alpha to be independent of X at every point in space-time, right? That was a global, that was a symmetry of the action. It would have been a global symmetry. But now what we want to do is that we want to make this, promote this to a function of space and maintain the fact that it's a symmetry. So it leaves the action invariant. But now what we're going to say is that this is a redundancy of the description. Meaning what? Meaning that here's my fiber bundle where M is just a line. M is just a line. And X is S1 at every point. So the value of the field at each point is like is a point, right? So here, oops, this is, I realize that this is a bit poor drawing. You understand what I'm saying, right? This is the value of the point. It's an angle around this circle, right? This is called a section in this fiber bundle. Now, when we say this is a redundancy of the description, it means that physically there is no difference between this section and another section that's like this. So at each point, I can trivialize these guys. I can move them arbitrarily, right, and bring them to a point. So I could trivialize this at every modular subtlety that we saw. There were cases where we couldn't trivialize this, and that had to do with some obstruction, some topological obstruction. In Stokes' theorem, we saw that has to do with, we'll go over this, right? We'll repeat it very quickly. But that's what a gauge redundancy was. Symmetry is a misnomer, right? It's just a redundancy of description. They're unphysical. These transformations are unphysical. They do not act in the Hilbert space. It's just, do you remember why we even introduced them? Why do we introduce them if they're non-physical? Exactly, precisely. Because gauge theories are these theories that secretly, well, they have non-local observables. But we wanted to still describe them locally because we love locality, right? And that forced us to introduce these redundancies, right? And what was the name of these non-local observables? Wilson loops. Awesome. All right, so good. So what is a gauge field then? The gauge field is a connection. So let me remind you what a connection is. I said that here's a point here's a vector field. This is the field at one point in space-time. I can apply transformations, right? Move them around. But in the action, if you recall, there's a kinetic term. The kinetic term involves taking a derivative of the field. A derivative of the field would require comparing the field at two near adjacent points, right? Nearby points in space-time, right? Now, if I had only just a real scalar, there was nothing to worry about. But here's a point. There, like at these two different points, I have two different spheres, and I have to decide which point goes to it. Like I have to identify these to be able to subtract them, right? And there are many choices of identification, right? Every choice of identification we give them a name. I have to transport the field phi from here to here, phi I from here to here, so that I can compare them and subtract them to define the derivative. This is an absolute must. Otherwise, I cannot define derivatives. The transportation rule are these Wilson lines. We define these guys, right? It's just like some object that moves you from here to here. Now, when you take derivatives, you immediately realize that, well, this derivative, we define covariant derivative, right? Which is what when you take derivative, it will depend on this W. So W is a function of 2 points, endpoint and initial point. It will involve the expansion of this guy when epsilon is small for nearby points. And the first order coefficient of that is a field that is called a gauge field. It's a connection. Geometrically, we call this a connection. It's something that allows me to compare nearby points, right? Of course, it carries these labels, ij's. Now, I mu of x, right, lives at each point. So, or I'll say, I just wanted to remind you that it lives at each point, right? So, for example, this term tells you that when you have, sorry, I said a mu of x, it will tell you how, it's like a rule that will tell you at this point, you move phi, rotate phi in a particular way. But you don't rotate it. This is in the tangent space around this point. Because your nearby points, your field phi moves very slowly. So these two vectors are so close by that this is in the tangent space around that point, and that has a name. It's tangent space of Lie algebra. That means that the gauge field is Lie algebra valued. Right? Good. So it's a connection. Hopefully, questions? We went through these in absolute gory detail last semester, but if there are any questions, please ask. If you want to catch up and you haven't had the chance to lectures from last semester, you could also look up Piskin or any text. Good. Now here, there are two labels that I'm using to describe this guy. But then we said, well, here's a tangent space at each point, right? It's easy to pick a basis, right? This is a group. I'm going to define a trace for it. And I pick these orthogonal this becomes an inner product for my Lie algebra, right? And this half is usually conventional, right? And these guys provide a basis for my Lie algebra, for the tangent space of my Lie root. This is I'll try to, I think last lecture I was for a second I used the index A for ij's, and that was a little bit confusing, so I retrieved it instantly. So I try to clarify, right? So every time I write lambda of A, that's a matrix, right? And then it's a Lie algebra. So Lie algebra will tell you that there is this commutator property, right? This antisymmetric thing, the coefficients of which are called structure constants of the Lie algebra, right? Everything about the Lie algebra is encoded inside the Lie algebra, is encoded inside the structure constants. Now, whether the Lie algebraic structure is sufficient to construct a Lie group, what's the answer to that? No, it's not. What's an example of this? We saw Lie groups that had the same Lie algebra, right? Yeah, exactly. So this is like when there are global issues. When the tangent space is insufficient, well, yeah. When you had multiple covers, we talked about this, right? Universal covers, blah, blah, blah. This is actually, this is one of the key ideas in constructing representation theory Lorentz group for us, right? We want to represent SO3, 1 plus, we use the representation theory of SU2 cross SU2, right? Went through universal cover, all that song and dance. All right, so a familiar example just to orient yourselves. If the group is SU2, you're dealing with a bunch of unitaries, right? That are 2 by 2 complex matrices. Oops, I did it again. IJ. Now, a basis for a little curly SU2, this is the Lie algebra, are X, Y, Z's, right? Why is there no identity there? Because it's SU2. If I had U2, there would be the identity there. Right? You remember what this deal was? We made a huge deal out of this, right? But there's no identity for it. Okay, good. Very good. Any questions so far? For those of you guys who haven't, we went through this in detail in last semester, but if there's some step that is ambiguous, please ask. Yeah.
Can you just tell me, like, in the previous slide, like, there was an index J. Can you elaborate on that? Like,
Index J here.
yes.
So this is summation.
Before, okay.
Where?
No, I get it. Like, when we are defining the derivative,
Yes.
like, just kind of scroll up a bit. Yes. So, like, are we considering single Wilsonian loop over there, or between two adjacent, or we are taking two adjacent points and then defining Wilsonian loops on those?
So it's just called Wilson loop, right? Wilson loop is just some transformation rule, right? It's a function of the endpoint and then the initial point, not the path,
Not
right? It's essential. If I want to define a derivative, right, it should not depend on the path, right? So it has to be a function of the 2 points, and then smoothness and a lot of other properties tell me I can do this expansion. It's a Wilson line. Sorry, I said loop. Oh, Wilson line.
and
But it's a transport. Sorry to interrupt. But in general, right, this is a route to defining connection. Whatever physicists call it is a different thing. This is a transport, right? It transports a vector from here to here.
And in that U of ij of x on the topmost line, like
Yes.
one index is for the vector, I understand. What is the other index for?
So this U is a matrix, right?
Yeah,
Because it involves
yeah.
rotation of this guy, right?
Right.
So yeah, it's a linear transformation in a vector space. SU2, think of SU2, right? So phi I is a complex two vector, right? And so SU an element of the group is 2 by 2 unitary matrix, right? So in this analogy, phi I is charged matter, right? For SU2, or for say U1 of gauge theory, this is just complex field, which is the spinner. Right? Spinners are chalk. Matter, electron field in QED interacts with gauge fields, right? So I repeat, the whole gauge theory, this business came out of the fact that we had a vector field, we had a field with a bunch of indices, and we needed to define a connection. And then we realized that that connection cannot be trivialized always, right? Because there could be some issues regarding curvature. Right? The connection has a curvature. The connection itself is not fully physical, but the curvature is physical. So, good. Any other questions? Sorry, I'm just pushing this up and down constantly. I have missed an important meeting today. I don't want to do it again. Keep looking at my watch, my phone. All right. Questions?
For curvature, then there should be a metric associated with that.
Say it again.
If you have some curvature, there should be a metric associated with that.
Yes. Yes, correct. So there's a metric you could point. Yeah. There's a canonical metric you could write down for these Lie groups. If you look at the formal study of Lie groups, it's often used intensively. All right. So this is we made actually an analogy between this and general relativity in case you have seen it, right? So the connection over there is the Christoffel symbols. That's not necessarily physical. Well, there's some physics in it, but Christoffel symbol cannot be. There's some coordinate dependence in it, right? Over there, what plays the role of these gauge redundancies is coordinate transformation, diffeomorphisms, right? Yeah, let me not confuse you guys with gravity. All right, so we define this business of connection allowed us to define the notion of parallel transport. By definition, parallel transport, so we made a choice of a connection. Parallel transport that tells us how to compare. Parallel transport is a statement that now that you have a rule to transport without changing the field. Right? Just this is parallel transport. What is take the value of the field here and just move it around along this path without really introducing, well, just saying the covariant derivative equal to 0, right? This is the covariant derivative, right? Just move it along. Just the point you identify. Right? So this is covariant derivative. Now here comes the physics of it. Every time you have covariant derivative, you could have holonomies. Holonomy is when you go around a loop and under parallel transport, you don't end up where you start with. So you start with this, you start with this vector, you parallel transport along this guy, then parallel transport along this way, the vector ends up this way, parallel transport along this, you end up, this is your final, this is the initial. So you went around the loop and you then come back where you started, right? Every time this happens, you have curvature, right? And the curvature, this going around the loop in this example is like, I've made it look like there are 3 legs to it, but you could make it, view it as a failure of the failure of multiplication of 2 covariant derivatives to commute, right? You take a step this way back, then one commute. This is curvature. So the curvature tells you how much they fail to commute. I put a factor of G down here. I might change my mind, but good. Any questions? It's just a review of what we've gone through. I felt like last lecture when I just jumped directly into non-abelian gauge theory might have been a little bit too quick. This is also quick, but hopefully it's a review. Now, Wilson loops. we said A mu of x, the connection is not an observable, but F mu nu is. If you remember from from electromagnetism, what is F mu nu? F mu nu is a matrix. It's 4 by 4. What's on the diagonal? Zeros, because it's antisymmetric. There are 3 E's in there and 3 B's in there. It's an antisymmetric 4 by 4 vector, tensor, sorry, 4 matrix. It has 6 variables, right? Do you remember how it works where they said, okay, you know this kind of stuff.
EX, EY, EZ.
Yeah, that's right. EX, EY, EZ, and minus ones on this side, and then BX, BY, BZ are this like triangular thing.
Which one is
Yeah.
these? I don't know. Go that way.
Yeah, so it's like, so this is 0, 0, right? 0, 0, 0. Minuses, right? These are B's. These are B's, I don't know. Feel like it out. Yeah, it's epsilon IJK, right? X, Y, Z, X, Y, X, the signs I don't remember. All right, okay, so that's what F mu nu is. It's pretty clear that we're gonna build out of this. Oh, actually, I just thought of a good homework problem. We're gonna build out of this, this physical, right? A Hamiltonian, Lagrangian density, all of that, not out of A mu. All right. So what's the Wilson loop? Wilson loop is like you go around the loop and you integrate dx mu A mu of x. If as you go around the loop, you could trivialize these fields, right? That would mean every time you trivialize it, it means like you're setting A mu of x equal to 0. Right? I could set it to 0 by trivializing. Now, if I could trivialize it, then I can go around the loop and trivialize it at every single point. It means that this integral is 0. Now, this integral by Stokes' theorem is related to F mu nu of x. This is d of A. Hopefully you remember what it was, right? Anyone wants to yell it? Okay, this is the simplest form of it. They're equal. Oh, for non-abelian, yes.
Yeah.
For non-abelian cases, there's a commutator. Sorry, yes. So for QED, they're equal. For QED, they're equal. Thank you. That was important. Good. So somebody is following more than I do. Good. So Stokes' theorem tells you that this integral around the loop is equal to an integral inside it's related to the flux that goes through this, right? This is the electromagnetic flux that goes through this. What's it called? Something that is inside the. It's not a disk, but you know what it. The surface. This codimension 2 surface. Codimension 1 surface. When the gauge field here is 0 inside this, the gauge field could be sorry. When field strength is 0 inside the loop, gauge field can be trivialized everywhere. When it's not 0, you will not be able to do this. So there's holonomy. This is precisely, we argued, this is a manifestation of the non-locality of gauge theories, right? The value of the field here depends on what's going on at the proper distance, at a point, in a point from it, which is spatially, space-like separated from it, right? That's a non-locality element. Good?
Still allows no signal.
Oh yeah, absolutely. Perfectly safe. Otherwise, otherwise things would have been very different. Yes, fully. What would be signaling? Commutator of physical observables, right? All right, I'm just gonna say it. So if you, oh, no, not yet. Next slide. All right, Yang Mills. So consider the action for a gauge theory with gauge group G, which is a Lie group with representation R, and Lie algebra generators T of A. The A mu and F mu nu are Lie algebra valued gauge field and field strength. The Lagrangian density we wrote down is trace of R, F mu nu, F mu nu. Right? So hopefully you recall that. So now that I can expand these guys in TAs and TBs. TA and TB by definition were orthogonal. There was delta AB in there. And the coefficient of that in the general representation is going to cancel this guy. That's the point of it, right? So you basically end up with minus 1/4 trace of R F mu nu A F mu nu A. Why minus 4? We usually for scalar field we normalize by minus half. Comes out of this anti-symmetrization square, 2 copies of it, right? That's where the origin of the 2 is. Very good. F mu nu is gauge invariant. You could check that explicitly. This action is gauge invariant, as it should be. Now, if you expand this action, here's a, like on the spot, I'm going to put you guys on the spot. What are we going to get? In terms of E and B's. E squared minus B squared. Minus, I'm not sure. But, well, Lagrangian this, yeah, maybe. Yeah, that's right. Yes, half. No, wait, sorry, maybe. That's right. Hamiltonian would be, that's right. B squared minus B squared, plus B squared, right? It's important that in this action, you did not get a term E dot B. Right?
That corresponds to the F mu F tilde, right?
Correct. We're going to discuss this term in detail. This is related to axions. This is related to some other topological aspects of gauge theory we haven't discussed yet. But it's crucial. This term could have been there, right? But it's not there in the action we wrote down. Just physically, we're going to later on write something. We're going to discuss like axions. Probably we'll discuss axions. And then over there, every time you get lost in what are these terms, F tilde we were writing down. It's all about E dot B. Well, once you get there, we'll comment on this. But
Just to cross check my understanding. But F mu F tilde, term is not forbidden by symmetry, right?
it's gauge invariant.
Yeah.
It depends what you mean by symmetry.
Okay, but it's not.
It's gauge invariant.
Okay.
There's no symmetry here. Well, we haven't discussed symmetries yet. Right? There's Poincare symmetry, but there's gauge invariance.
Is there a specific reason of not including this? It would be done in your action which you're defining, or the Lagrangian which you're writing?
I could have, and I did not. I did not, and nobody complained. I just wanted to say that I did not include it. There was a reason for that. Well, I don't think any of you guys took that course with me. I taught a course on topological phase of matter, and there's a detailed discussion of that over there. But there's some physics associated with it. But all I want to say is that you're asking why we didn't include it, because this was built based on QED. This is generalization of QED. In QED, this term is not there. Right? It was just E squared plus B squared as a Hamiltonian. So we're just generalize that picture. Also recall, well, I guess you weren't there, but in part 1 of the course, we derived this action in the low energy of a lattice model. And this guy popped up. Actually, a good idea to see how this could pop up is to go back to that derivation and see how you could have arranged for this term to pop up. All right, okay, enough for tangents. We're all good with gauge theory, classical gauge theory, classical non-abelian gauge theories.
So this will break
It will.
but like we argued
Yep, there was quite a bit of correct. So CP violation, we proved CPT. Right, actually, did we prove? I just said it. I just said it. Well, I know that how everything I can prove on the board, I consider that we proved in the class. Yeah, so yeah, CPT is a correct statement. Actually, technically CPT, I don't know, CRT is a correct statement. I said that? Oh, wow, okay.
You
Ah,
mentioned that.
I'm proud of it. I'm proud of myself. I'm proud of it. Okay. You guys are so good. All right. So now let's come back to part two, like part QFT2, right? So now what we're doing is last lecture we took this term. Let's forget about -1/4 TR blah 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 normalization G squared, all of that, and we're gonna take this for non-abelian gauge theory and expand it. We said that we're gonna get the standard quadratic term, right? This is the term that, oh, I erased it. Good thing I erased it. This is the term that I got before. There's 2 is for that -1/4. Then I get a term which is G. It has 3 interaction with 3 points, 3 vertices, and there's a del mu, right? That means the momentum. And then there is an interaction with 4 points, 4-point vertex, and no del mu, right? And this is G squared. So again, if you want to compare this to scalar field theory, recall how in scalar field theory, we didn't have a principle that fixed for us the relative couplings of these different terms, higher order interactions. Every term could have been different. There was no principle. We saw that in the case of nonlinear sigma model, that symmetry was the principle. Here's gauge invariance. That's fixing for us. This is G squared, and nothing higher. No other term higher. For non-abelian gauge theory. Good. There will be several terms. We're going to call these interactions. We're going to come back to them. Yeah.
So till now, we have not specialized the particular gauge.
Oh, that's going to be all about the rest of this lecture. It's all about, sorry, gauge group.
Yeah,
Oh,
like SU2, for example.
Oh, yeah, SUN. So far, like, just have in mind SUN. UN, SUN. Yeah, it won't matter. Yeah, the only thing I want you guys to have in mind, if I ever say something without specifying, I'm thinking of adjoint representation, and the matter is often fundamental and anti-fundamental. But I think I might this discussion today is like fully general. I'm pretty sure today is fully general. Good. So last lecture we talked about propagator on arc-C gauge. By the way, when did we do the arc-C gauge? I couldn't remember. Was it QFT1 or 2? 1, like last part loops. We're looping. Okay, good. So just to remind you, and it's a gauge that we introduced. There was a free parameter C in there, and the propagator in this gauge had this form, -I/k squared plus epsilon. Oh, by the way, sorry. Very, very important. I forgot to say. When we're talking about non-abelian gauge theory, I said that I think we're gonna draw this. We're gonna call I'm just gonna colloquially refer to the particle, the quanta of it, as a gluon, as opposed to a photon, right? I might colloquially call it that way. And it's labeled by 2 indices, right? And the same here. One of them is the Lorentz. So the 2 indices explain to you how transforms under symmetries. Well, space-time symmetries and gauge labels. They're not symmetries.
We call it gauge and symmetry, so redundancy.
Redundancy of description. It's not symmetry. It's very crucial. It's a misnomer. It's a very This old terminology and should be discarded. It's not my personal opinion as well, but like I think it's correct to just never call it gauge symmetry. So propagator in arc-C gauge had this 1 minus C in there, And this C, when it was 0, is Landau gauge. When it's 1, is Feynman gauge, and there's no physics associated with it. This means that this term has no physics associated with it. Why? Because the photon does not have a degree of freedom in the direction of its propagation. Right? There are only two polarization orthogonal to direction of propagation. Because it's massless. Right? Masslessness allowed for the representation theory. The representation theory of massless particles for the Poincare transformation, right, had only two velocities. Good. Physics has to be C dependent, independent. Now, today I'm going to make a big deal out of this RCC gauge. Go through, well, actually here. So today we're going to do the path integral quantization of non-abelian gauge theories. Whoops. All right, let me not try to summarize before going through it. Good. So what are we going to do? We're going to do path integral quantization of non-abelian gauge theories. Let's call M, this I've been using the term M other places. Give me a name. M tilde. Good. M was my space time. Well, this is M tilde. M tilde is the space of all gauge field configurations. Right? G are the gauge transformations. So M tilde is a fiber bundle, right? It's a point, it's a vector, yeah, it's a principal bundle, right? It's labeled by two things, the value of the field at each point, right? G is a gauge transformation that can trivialize this connection. So this is a connection, if you wish. So this is a connection. Maybe that's a better term. It's a connection. Sorry, I should say fiber. It's a connection. What we want to do is we want to path integrate over physical aids. But the issue is that our gauge transformation. So what we're going to do is that we're going to path integrate over all the space, all M tilde, space of all configuration, and mod out by the ones that are related to by gauge transformation, the volume of the gauge. Now, time is space-time volume because, yeah. Of course, there are divergences in everything, like upstairs, downstairs, it's all divergent, right? But Fadeev-Popov told us how to deal with this properly. So I'm gonna go over the philosophy and because it could get a little bit ugly. I'm gonna describe the philosophy first, and then go through the steps. So first, let's set the notation to understand what we're talking about, because I'm gonna heavily use concise notation. So let's just get this right. Take a gauge field, right? A mu of A. I'm just suppressing X dependence. Let me just put it back in. A gauge transformation sends A mu of X, A mu of A, because it's Lie algebra valued, to A mu of A of lambda, A lambda. This is the gauge transform version. This is covariant derivative, right? And lambda of A is the analog of that like gauge. So in QED, gauge transformation was sending A mu to del mu of some function alpha, some gauge transformation alpha of X, right? So that was some phase. Here it's lambda A of X. It's Lie algebra value, right? At every point. Well, it's Lie algebra value. So of course, and then this is covariant derivative, right? Which inside itself, yeah. Well, but then there's a catch. Well, okay, I'll not explain. But this is proportional to delta AB. Well, no, I did not say that. I did not say that. There's gauge fixing condition. Gauge fixing condition. For example, del mu of A mu of X equal to 0 or equal to some function minus omega a of x is some example of a gauge fixing condition. And I'm going to formally write it as g of a equals 0. More precisely, I'm going to use this equation. G of a lambda is equal to 0. It's a gauge fixing condition. It's a constraint I'm going to impose because lambda won't matter. In my path integral, right? What I'm going to do is I'm going to gauge fix. I'm going to integrate over the path. Instead of modding out by this, one way to mod out is just fix the gauge. Right? So that's what I'm going to try to do. We'll see. So how am I going to fix the gauge? I'm going to stick inside the path integral delta function of g of a that will impose g of a equal to 0 on every configuration. Right? G of a lambda. All right. So are we all good? This omega of x is just a generic choice of gauge. Instead of working with like omega a lambda equals 0, which was Lorentz gauge, I'm going to just be generic. We're going to see for a moment in a second. So before I start, are there any questions about this so far? Good.
Is this gauge fixing condition integrated locally or is it global?
Global. It's a function worth, right? So for a function omega a of x, I'm gauge fixed. I can pick my omega of a of x to be constant everywhere, to be 0 everywhere, right? But I don't have to. Good. So in step 1, so what are we gonna do? What we're gonna do is we're gonna massage this guy, integral of d of a mu of e to the power of I of s mu. This is the expression I want to calculate. Sorry, there are labels of a all over the place. You know what? Right? This is not a billion. I want to write this path integral in the following way. I'm going to look at the measure. This measure has plenty of redundancies. I'm going to split this measure as a path integral over lambda of x, a function worth. Of course, it carries like these lambda label a's, right? Of gauge transformations, and then the gauge fixed ones. Right? So this is, I have an integral that is overcounting the gauge. There are all sorts of gauge redundancies. I'm going to write this integral as an integral of the gauge fixed thing multiplied by the other stuff. Now, dividing by gauge redundancies is just dropping that multiplication. Right? So this guy is gauge fixed now, which means that I'm going to stick inside this. So this is a lambda of a mu. I'm going to stick inside this path integral, g of a mu lambda of x equal to 0 as a Dirac delta. That's my goal in step 1. Logically, it makes sense. I haven't done it yet, right? We'll see that it will involve some manipulations of like path integral functional manipulations that we'll learn about in QFT1. Right? So we do that first. In step 2, because here what I did was that I introduced some omega of a. I've gauge fixed in a particular way. And because this is gauge fixing, I could take this answer with gauge fixing choice omega 1, calculate this for omega 2, the answer is equal, right? I can path integrate over omega a's with a measure that integrates to 1. So this is averaging over gauge conditions. I'm allowed to do that, right? Because they're all equal. The functional integral does not depend on the averaging on the gauge condition, right? So I can integrate, I can average it. This normalization makes sure it's average to 1.
Doesn't the average go around the circle average?
Huh. I separated them. One of them, I put lambda and gauge transformation of the field, right? And then on top of it, I impose gauge condition. There's a reason I'm doing that. It might seem redundant, but like the Fadeev-Popov actually relies on this splitting. you'll see, like, it collapses. This integral will collapse. These integrals will collapse. So far, I haven't done anything illegal, right? Now, I plug this as an integral, as you just said. Now, I do a bunch of manipulations, and I perform the integral, path integral over omega of A. What happens? This C that I put in here turns into arc C gauge. We'll see this, okay? So this in path integral will impose the arc C gauge. So this is a choice of gauge. Oops, this is a choice of gauge, right? There are all sorts of other choices of gauge. The relation between this choice of gauge and arc C gauge is that arc C gauge is this particular average over these choices. Right? This is all like unphysical stuff. But we'll see, it will be very, very important. All right. We saw that actually the way we argued for arc C gauge, if you recall, was that I added to the Lagrangian this term. We're going to see that performing this integral, massaging things, will give me this term in the Lagrangian for QED. For QCD will give me the same term with an A. But for QCD or non-abelian gauge theory, it will give me extra junk that drops out in the case of QED. That extra junk is this. It's a determinant that we interpret as ghosts. So what is this thing? In the case of QED, we perform the path integral, we get a local action that will do the job of gauge fixing for us. Everything is good. For the case of non-abelian case, we write this as a local action, but there's still some stupid function, determinant of a function worth inside the path integral. So that local action doesn't quite gauge fix. So one trick that we use is that we take this determinant and write it as an exponential, as an integral. Then we pull it back up to the exponent, and the job of that extra term that we add to the action is to just properly take care of this determinant. Now, this determinant that will as we write it as a path integral, right? We'll path integral over some fields. Those are called ghosts. The reason they're called ghosts is that the only role is to make sure this determinant is essential for normalization of the path integral, for unitarities. So the probabilities add up to 1, right? Turns out that the job of these ghost fields is going to be just making sure everything is properly normalized. And it's absent in QED because we're going to see that this determinant is a constant in QED. It's field independent. It just comes out of the path integral and becomes part of the normalization. No problem. There's no functional dependent. So that's what we're going to observe in Fadeev-Popov. Are there any questions about what we're going to see? And we're going to see it. I'm running really slow. Good. All right. So let's go through this. First, a bunch of functional identities. If I have, this is just a simple integral. Integral d lambda delta lambda is 1. Now I can write down this guy as delta of g lambda del g del lambda norm of it d lambda. Right? I'm allowed to do that. That's just like a simple differentiation of the direct delta function identity. Now, if this were n dimensional, some large capital N, this has nothing to do with the other n's we have had in this course. I have these lambda i's. So I'm going to do an n-dimensional version of this that I'm going to view as a vector. Right? Now this is a vector. This function, I'm going to consider to be this is like a map from vectors to vectors, right? So, right? So this is also a vector. I put in a vector and get a vector. So it's like a linear transformation, right? So the analog here is this one, the analog of this, once it's n-dimensional, becomes 1 is equal to integral of I d lambda I, determinant of this linear transformation, the n-dimensional delta of this guy. Right? Good. Now let's take the continuum limit. When this vector lambda becomes lambda of x, a function worth of things, then this g becomes a differential operator. Right? Sends a function to a function. That's going to be a gauge fixing, like del mu, blah, 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 right? So my identity, functional integral identity, becomes the path integral over lambda of x times delta of g of a lambda is del g a lambda d lambda. This is that determinant. This thing is that determinant that and QED is independent of the field. So it's just a constant, it just comes out of the path integral, but in non-abelian gauge theories, will be field independent and we'll have to treat with it. Right? It's just a Jacobian of identity. Ghosts are just coming from the fact that we have this Jacobian of identity that we have to deal with to make sure everything is properly normalized. We write it in an exponent. And so determinants, if you recall, could be written as path integrals, Gaussian path integrals, right? The things you path integrate over are these ghost fields, right? All right. Good. So what is a lambda of a mu? Here's the expression for it. So I want to compute this guy. This is a lambda of a mu. G of a lambda is linear in a lambda. Recall what it was? For instance, this was del mu of a mu minus omega was 0. It's linear. That's the only thing that matters. It's a linear operator. This means that when this is also linear, this differentiation, this comes out of the covariant derivative, and this depends only on the covariant derivative. So it's independent of lambda. So I think I was just gonna do this calculation for the case of U1, but I forgot to finish it. This is independent of it, right? So this guy is independent of lambda. I can bring it out. That's what just concluded. Why? Because the gauge fixing conditions I'm using are linear in lambda, in A. All right, good. So here we go. So far, what we have is, so I have d of a, e to the power of isa. I plug in integral of d lambda. This guy was inside this guy. I just pulled this out. Right? I just inserted multiply. I just put this identity inside here. And I notice that I can pull this out. Now, this does the gauge fixing for me. Right? Because delta is here. This does the gauge fixing for me. So let's, for now, look, for simplicity, let's deal with QED. Let's deal with QED. Okay, sorry. This does not come out. Only in QED it comes out. Let me clarify. Sorry, I think I got this. I specialize in QED without explaining. So what I have is this expression. This is just, I inserted, oh God. I inserted 1 inside the path integral, right? Then I argued I can take this guy here, right? This is independent of lambda, so I can pull this out. In QED, this is also independent of A. I can pull it further out. Why? Because in QED, this is just determinant of 1 over E del squared. Right? It's just a divergent quantity that on my manifold, and it's just like, it's independent of the field, it's independent of the gauge field, it's independent of everything. I'm sorry, independent of the gauge choice, it's independent of everything. So it's an overall constant that comes out. What have I achieved in the case of QED? I've achieved the following expression, d of a mu e to the power of isa. This gauge fixes to omega a, and there's d lambda. Here. This is A lambda as well. Notice that here I played a trick. So sorry, let me be a little bit clear. So this is I'm just gonna do this properly. I did this way too quickly. So this was delta of G of A lambda, right? So this is A lambda. Gauge invariance tells me that these are the same things up here, right? S of A and S of A lambda are the same thing. That's gauge invariance. Gauge invariance also, if the measure is independent of lambda, then I can replace that. We said that classical field theory is gauge invariant. For the quantum field theory to be gauge invariant, it meant that the measure had to be gauge invariant. Otherwise, we have anomalies. We also said that it doesn't make much sense to have gauge anomalies. So this is going to be here, but you could check explicitly. Why is this? What is a gauge transformation? It's just a shift of A mu. It's a linear shift of A mu, right? For QED, so it just comes out. For QCD, it's a shift and a rotation. Again, linear comes out. The measure will be independent of it. So what did I achieve? Now, once I replace this here and this here, this looks like a gauge fixed integral. So I wrote my path integral as a path integral over the gauge fixed configuration and integral over d mu. I delivered on the promise for step 1. Good? Is this good? In the case of QCD, everything is the same, except or non-abelian gauge theories, that this stays inside here. So I'll have to deal with it properly later. In step 2, what we do is we said, so here's omega of x. I'm going to path integrate over omega of x with this measure. So I just put everything next to each other, perform the path integral. This comes out, this is n mu d lambda. If I path integrate over d omega, and this is where the omega dependence is, the other omega dependence is here. What is this path integral? Yes.
So wasn't omega Leon Bernoulli? Was it?
Yes. I'm doing QED now.
Oh, okay.
Yeah. We'll come back to that. Thank you. This is QED. I should have clarified this very clearly. I'm doing QED.
No, we're still doing QED.
Yeah, we're still doing QED. I put this outside, right? Like.
Oh yeah.
This part I can perform path integral and gives me this 1/2 sigma del mu a mu. So this is the origin of the RCC gauge. Why? Because this is unimportant. This is unimportant. This is unimportant. These two are constants. This is just like volume of the gauge times volume of space-time that I want to discard. So it's all good. This is the origin of the RCC gauge. This is QED, right? We want to do this exact same thing for QCD and get to your question. All right? So let's repeat this for non-abelian gauge theories. So in non-abelian gauge theories, as we just said, omega has an A index. We already know what the 2-point function in the RCC gauge is going to look like. It's going to look like this, right? It's just delta AB. In Yang-Mills, if you look at now I want to find this operator, this determinant, annoying determinant thing. Now, when I calculate the annoying determinant thing, I'll get 1/g del mu of d mu covariant derivative. Now this guy depends on the field, gauge field, and I cannot bring it outside of the path integral. In fact, a good way to deal with this is to take this determinant and write it as a path integral over dc bar. These are anti-commuting fields that belong to the adjoint representation and scalar under Lorentz transformations. Anti-commuting. Yeah. This is an identity for anti-commuting fields that are adjoint representations under the gauge group and scalar under Lorentz transformations. Why should they be anti-commuting? If I just replace these guys with commuting fields, what's going to be different?
The result is only inverse.
Yeah, I'll get a -1 up here, -1 here. Beautiful. Yeah, that's the reason that they came out to be anti-commuting is that I got a determinant, not determinant to the power -1. Beautiful. So these are called Fadeev-Popov ghosts. This term that we add to the Lagrangian, we have to add this term to the Lagrangian, and we have to path integrate over the gauge ghost fields. This added to the Lagrangian is called the Fadeev-Popov Lagrangian, right? This is the ghost Lagrangian. Let's expand this. This is C bar of A minus del squared, right? Del squared, del AC. So it's diagonal in those labels. Minus G del mu F ABC. The structure constants. The structure constants are the place that, because in non-abelian gauge theory, the structure constants are non-zero, there will be a dependence. And it won't come out of the path integral. Therefore, the ghost will have a vertex with the gauge field. It's a CC bar ghost, CC bar gluon, CA C bar A gluon vertex. Right? Actually, but wrong, sorry. Wrong. I'm going to draw it in a second. C bar gluon. What is this vertex going to be? Let's just copy from there. F A B C has to be contracted, right? So here gluon is mu C, right? This guy is going to be A, this is going to be B, right? There is a del mu in there, which is going to be the P mu, which will contract with this. Right? I'm gonna show you and I rescaled the ghost because I can by a factor of over G to bring this G up here. But the job of these guys, these ghosts can never be external legs. Right? It's an expansion of path integral. They're never on shell. These are things that we just determine some stupid determinant path integral, and I wrote it as a path integral. They're not actual particles. Right? It's an integral. It's just an integral, right? And so these guys cannot be on shell. They're always in the loops and doing stuff in the loops. And when they're in the loops, their job is to cancel a bunch of positive terms. Right? To cancel some probabilities, to make sure everything is proper. Right? Every time you have these guys, it's just keeping track of normalization is their job. All right, so here's a 2-point function for the ghost, anti-ghost. This is the full action that you're dealing with in the presence of the matter fields, gluons, right? So here's well, I'm just suppressing everything. Hopefully it's clear. There are like traces and stuff, but hopefully you understand all of that, right? So F mu A squared, this is the arc-C gauge term. This term is with the proper indices, this D is D slash, right? And these are the gluons that carry also a label, right? C bar of A, C of C, this is the dA mu of AC. Now, we're gonna, because we're running out of time, we're gonna write down all the vertices for non-abelian gauge theory in the next lecture. But I just want to point out that these are the two vertices of the ghost, right? This is the propagator for the ghost, and this is the vertex I was just writing on the board. Right? This P mu has to do with the fact that there's del mu here. There's del mu here. Good. All right. In summary, in QED, we fix the arc-C gauge by adding this term to the Lagrangian. If you remember, the way I argued for this was reverse engineering from the on-shell action. I said I want to shift one. I want to change the coefficient of the propagator to 1 minus C. The propagator, the way I found it was by inverting the on-shell action, right? So I said, oh, if I want a 1 over C term over there, it should come from this term. If I want a C term over there, it should come from 1 over 2 C. That's how I reverse engineered it. But in Fadeev-Popov, we derived this in a very systematic way that could be generalized to non-abelian gauge series, and we saw that how this whole procedure led to ghosts, right? All right. So in the non-abelian gauge theory, we systematically did this. Fadeev-Popov, the key ingredient was integrating over different gauges with an averaging over different gauges, right? With this weight that was C dependent, and that C of the weight, because it's up to me how I average, imposes a gauge. There's in non-abelian theories, there's a leftover determinant term. This leftover determinant term is there in a abelian case as well, but it's just a constant. In the non-abelian gauge theories, it depends on the structure constants and has a mu in it. Right? That means that there is some and then we exponentiated this, put it as some sort of trick by introducing some ghost. And this is the origin of the ghost terms and Fadeev-Popov Lagrangian. I think this was supposed to, so wasn't supposed to be there. All right. So this is what we did. Any questions?
So in QED, what basically they see that if it tries to equal the Fadeev-Popov ghosts, basically see that the ghost part of the Lagrangian is completely decoupled from the rest of it. That's why we can ignore it. So
In QED.
QED.
Yes. All right. Any other questions?
We saw that we're trying to what do you call it? We're using the gauge condition to be like a del mu a mu is equal to omega, so to say. Would other gauge conditions have different would all of them lead to the same results or
Different omegas? Of course.
No,
Yeah.
like not have a del a is equal to something condition. We have some other.
Yeah, of course. But yes, but this is a convenient choice. It's like, well, yeah, it's convenient. It's very, very convenient. If you recall, the reason it's convenient is that its modification, this gauge dependence, this C term. When we wrote the propagator for photon or for the gluon, it looked like the standard term. The issue it had was that it was not invertible, right? All the point of arc-C gauge is that it just makes it manifestly invertible, right? So that's why arc-C gauge is good, and that's why this is convenient. Now, of course, you could do this in all sorts of gauges, but the nice thing about this is that you go around invertibility.
This is like the simplest way to get how things work out.
Yes, but of course, to make it invertible, you have added imaginary stuff. Ghosts, cancel those. Right? The proper amount they cancel. All right. So where are we going with this? Next lecture, I will start with setting up the Feynman diagrams, right? And we'll say a few words about, well, actually not next lecture will not renormalize this and we'll not do calculate the beta functions. I'll first go through the BRST symmetry. So by now, if you are not confused, you should be confused. This whole business is very weird, right? How these ghost fields keep track of unitarity seems a little bit weird. Or like at least not opaque, like it's not very clear. There is a symmetry of Fadeev-Popov Lagrangian. It's called BRST symmetry. Now, BRST symmetry makes the following connection obvious. So when I was talking about, recall when we were talking about gauge invariant theories, I said there's some form of non-locality, there's non-locality in them, but they're not any non-locality. They are sort of like topologically non-local. There's some sort of topological structure. So to see the connection to topology, BRC makes that very clear. So it will be about closed sequences and like basically the old, I don't know if you guys are familiar with topology, but like it makes a connection to topology very clear. So we'll go through that. We're gonna renormalize and calculate the beta function of non-abelian gauge theories. Then we'll probably talk a little bit about confinement. Turns out that the fact that QCD is genuinely interacting in infrared is good and theoretically challenging. What is the coupling of Yang-Mills in 4 dimensions? What's the dimensionality of it? Naively. It's marginal, right? If it becomes relevant, right? It means that it's going to grow. Also, it means that there will be scale in a sense. So there is a scale that's classically not there. It's quantum mechanically present. Quantum mechanically introduced it. This is an infrared scale. This is lambda QCD. This is a regime at which, so you remember lambda pole of QED? We're saying that in somewhere in the UV finite energy, it becomes insanely complicated. QCD is the same way, but in the infrared. So there's lambda QCD, where the theory becomes strongly coupled. That's why the universe is interesting. Because QCD is strongly coupled, so quarks form strongly bound states, and we have all sorts of diversity, like we have periodic table, a lot of interesting stuff. If standard model of particle physics was weakly coupled in the infrared, it would be just like a bunch of flying particles from here and there, right? The universe would have been boring. So this strong coupling is going to be very important, and there's confinement, an unsolved problem, and so on and so forth. Yeah.
Is that why you don't find quarks, loose quarks? So they're only